and depth limited expected max.
First, a quick recap. We are considering a toy problem, and it's that of the grid world. Just to let you in on a secret, it's a trade secret. Grid world, as simple as it looks, is still one of the main benchmarks of research in reinforcement learning and developing new reinforcement learning algorithms. So I know it looks simple, but it's very useful in exploring and investigating different aspects of Markov decision processes and reinforcement learning. And another secret I'm going to let you in a bit early is that Markov decision processes are the foundation of reinforcement learning and deep reinforcement learning, which in my opinion constitute the cutting edge of the state of the art in artificial intelligence. So we are building up to a very, very interesting topic at this point. Okay, so grid world is a maze-like problem. The agent lives in a grid, which looks like this. The walls block the agent's path, so the agent cannot pass through walls. The environment is noisy. This is really important. So actions do not always go as planned. In this particular toy example or toy problem, we assume that 80% of the time the action north takes the agent north, 10% of the time north takes the agent west, 10% east, and similarly for other actions. The agent receives rewards each time step. So at each time step, the agent receives a reward, and that reward is a scalar value. And there are two very big rewards. One is a positive reward, getting the diamond has a positive reward of +1, and a negative reward of -1 associated with falling into the fire pit. And these two states are considered to be terminal states. When the agent gets to these states, the game ends, essentially. The game is over and the agent doesn't have any more decisions to make. What's the goal? The goal of this agent is to maximize the sum of discounted rewards. Now, another quick recap. Markov decision processes are comprised of a set of states S, a set of actions A, the transition function or the transition probability, which is alternatively called the dynamics of the environment, the reward function R, and a discount factor gamma, and similar to our search formulations, a start state S0. We defined 4 quantities. We defined a policy, which is a function that maps a state to an action to be taken in that state. The utility, which is a sum of discounted rewards. Value of a state, the expected future utility from that state. And Q values, which are measuring the usefulness of particular actions in a particular state. Now, we've already talked about this just a few minutes ago, so I'm not going to go over this again. We talked about the example of calculating V star using value iteration in grid world and Q star calculation using value iteration or Q value iteration as well. Now I'm going to dig in deeper into the iterative recursive formula to come up with a more concrete, more useful formulation to solve MDPs. Now, this is really interesting. I remember my brother, who's also an AI researcher and is older than me, one day came to me and told me I've solved the AI problem. and I was in elementary school back then. I said, what do you mean by that? He said, I found the algorithm for general cognition and thinking. I said, wow. I was very naive back then. I thought he had all the answers. I asked him, so what is the algorithm? He told me the algorithm is to take the next optimal step. And this is essentially what Bellman equations and dynamic programming are all about. There are two steps associated to finding an optimal solution. Step one, take the correct first action. And step two, keep being optimal. Now let's see what we mean by this joke. Let's try to make it a bit more formal. So the definition of optimal utility via Expectimax, via the Expectimax recurrence, gives a simple one-step look-ahead relationship amongst optimal utility values. Let's look at this one here. We have, we've already seen this. We can reformulate or rewrite V star of S as max over the A parameter, the action parameter of the Q star function. And the Q star is defined as such, which as you can see depends on the value of the next state, S prime. So combining these two, we get this recursive formula, V star of S, the recurrence formula, V star of S depends on V star of the next state. These are known as the Bellman equations, and they characterize optimal values in a way we will use over and over. Bellman equations are very famous. They are one of the cornerstones, one of the pillars of discrete control. They are one of the pillars of dynamic programming or applied approximate dynamic programming. And they keep coming up as we go along, as we go forward in this course. And even if you stay in AI and want to do AI research, especially in reinforcement learning, Bellman equations essentially form the foundations of reinforcement learning, even deep reinforcement learning, such as deep Q networks, which we'll get to talk about next week. So Bellman equations characterize the optimal values, and value iteration computes the optimal values. Okay. So the Bellman equation tells us what the characteristics of the optimal value function should be and keeps updating the optimal values. And through value iteration, we calculate through bootstrapping, through this recursive or recurrence formulation, we keep coming up with, we keep approximating these optimal values. Value iteration can be seen as just a fixed point solution method. So we are trying to come up with an accurate approximation of something through fixed point solutions. But also, you can think of the V sub k vectors as time-limited values. Now that we are familiar with value iteration, and let me add that we'll be coming back to value iteration in our discussion on reinforcement learning, let's talk about a new set of methods called policy methods. First of all, how can we evaluate a policy? How can we check to see how can we come up with a metric or a number that tells us how good a policy is? So if we have a fixed policy, all we have to do is to start at point S apply the policy, which gives us the action that needs to be taken, and follow the expected max tree and come up with the optimal values. It's like evaluating the root node via the value of the root node in expected max. If we fixed some policy pi of s, then the tree, the expected max tree, would be simpler. Why? Because instead of all of these different action routes, we'll only have the choice of action prescribed by the policy. However, the value of the tree would depend on which policy we fix. So if we have multiple policies or evolving policies, the value of the tree will depend on our choice of the policy to follow. Okay, so what's the point? We want to use this concept to calculate the utilities for a fixed policy. If we have a fixed policy, and when I say fixed, I mean it's going to remain the same from the start until the end, if there is an end. We're not going to change the policy. It's always going to be the same function, not the same value or the same action. Note that the policy is a function. It receives the state as its argument, and it tells you what action to perform in that state. And since it's a function, it has a one-to-one mapping for all states to their corresponding prescribed actions. So how do we come up with utilities? How do we compute utilities of a state S under a fixed or generally non-optimal policy? We define the utility of a state S under a fixed policy pi with V super pi of S. Remember when pi was the optimal policy, we denoted this with V star of S equals the expected total discounted rewards starting in S and following the policy pi. Okay, so how can we calculate this? We can use the Bellman equation, which is essentially the recursive relation with one-step look ahead. Why do I call it a one-step look ahead? Because it's essentially just looking at the bootstrapping operation is dependent on the current state. The future state is only dependent on the current state. We don't go deeper than that. That's why we call it a one-step look ahead. So we can calculate V super pi of S using the same formulation, but instead of V star of S prime here, we have V pi of S prime. Okay, let's look at an example. Let's look at an agent in the grid world that's set up like this. And what the agent is holding is a policy. It's like a map that tells the agent where to go in each grid cell, which happens to be each state as well. So look at this policy here. It tells the agent to always go right. In the beginning, if the agent goes right and the action actually ends up being implemented, so even with 20% probability of ending up performing another action, it goes into the correct or intended location, it will always burn. Now let's look at another policy. Always go forward. Which of these two policies is better? Probably the one that keeps the agent alive longer. Probably the one that keeps the agent out of the pit of fire longer. So I would say this policy is preferred to this policy. Always go forward is a better policy than always go right. Now, let's look at it from a numerical or quantitative perspective. So there are numerous terminal episodes in these examples. There are the fire pits on the sides. Each is a terminal episode and comes with a reward of -10. And then there is another terminal episode, the green one, which is not a pit of fire. Maybe that's where the diamond is, with a value of 100. Now, if we apply value iteration to calculate each of these policies, we'll see that the value of these states are substantially lower than the values of these states here. Okay. How do we calculate the V's for a fixed policy pi? Well, the first idea is to turn the recursive Bellman equations into updates, like value iteration. So just like before, when we wanted to calculate the optimal values, or yes, the optimal values, here we say we are calculating the values of states based on policy pi. In k equals 0, which means there are only 0 time steps left. Every state gets a value of 0. And then we keep iterating over this formula and incrementing the value of k. This is what we had before. We've just changed the v star to v pi, which means that instead of following the optimal policy, we are now following the policy pi. Okay, what's the efficiency of this algorithm? The complexity of this algorithm is of the order of s squared. So we have to calculate this summation in the worst case scenario s times, because the number of states state s can end up in the worst case can be the size of the state space. It may end up in all available states. And we need to repeat this process for all s's. That's why the worst case complexity of each iteration of this algorithm is in the order of s squared. The second idea is that without the maxes, the Bellman equations are just a linear system. Notice that we don't have that max over A here. Why? Because we are not trying to find the optimal values. So we are not trying to find those A's, those actions that if taken at state S, we expect them to result in a better contribution to the utility. We already know what actions are going to be taken by the agent. How? We know the agent is following this fixed policy pi. This fixed policy pi is always going to give us a fixed action A for each state S. So we don't have that max anymore. Now what we have here is essentially a system of linear equations. And if you recall from your numerical methods or linear algebra classes, if you've had any, you've probably encountered this before. You can solve a system of linear equations quite easily. You can use, for example, MATLAB. You can apply the Gaussian method, for example, to solve the system of linear equations. Now, just a quick note here. This idea is valid, but when we're dealing with more complex systems, with large state spaces, it may become infeasible to apply in practice. We'll talk about better solutions when we start our discussion on reinforcement learning. Now, let's talk about policy extraction. how can we compute actions from values? If we have V star of S, how can we find the actions to take? How can we extract an optimal policy from V star of S? It's not obvious. We need to extract the policy from value function. We need to do a mini expected max, a one-step expected max. How? Well, the optimal policy for state S should give us an action. That action is one that maximizes this sum of expected rewards, discounted sum of expected rewards, or expected sum of discounted rewards. That's a better order of these words. What does this argmax mean? It means that give us the A, the action, that maximizes this value. How's that different from max over A? Max over A means that find an action that maximizes the value of this, and then give us the value. Argmax, argument max, means find the action that maximizes this value, but instead of the value, give us that action, give us that particular parameter. Okay, so this is straightforward. This comes from the definition of V star of S. Remember the definition of V star of S? We used Q star of S and defined it, and then substituted that definition into the equivalency of V star and Q star. Okay, so can we solve this? Yes, we can. And this process is called policy extraction. Why? Because it gets the policy implied by the values. Now, let's see how we can compute actions if we have the Q function. Let's assume that we have Q star, we have the optimal Q values. How should we act? This is really simple. It's really trivial. Why? Because then pi star of S becomes argmax over A of Q star S and A. Essentially, now that we have the Q star function, iterate over actions and give me that action that maximizes this value. Then that's going to be the output of the optimal policy for state S. As simple as that. Now, here's an important lesson. And this lesson reverts from even the current heights of AI research, especially in deep reinforcement learning. Actions are easier to select from Q values than values. So it's easier, more computationally efficient to extract the policy from the Q function instead of the value function. Now, this is, I think, the last concept we are going to cover in this session. There are a few problems with value iteration. Value iteration repeats this Bellman update, right? You remember this Bellman update? We talked about this towards the beginning of this segment. The first problem is it's really slow. We've already talked about the complexity. It's in the order of S squared A per iteration. And you typically need to run this for a large number of iterations. The second problem, the max at each stage rarely changes. So going from iteration 100 to iteration 101 does not really change this maximum. In the beginning, these changes can be significant, but as we move forward, as we move along in the number of iterations, the changes become smaller. So it's not surprising that the policy often converges long before the values. What does this mean? It means that the policy, the function that tells us what action to take, stabilizes sooner than the actual values. It means that we could probably stop the value iteration process earlier and get the same result. We can save some computation time. Let's look at an example here. So this is grid world, same settings as before. We have 20% chance of error or noise. We have a discount factor of 0.9, and we have 0 living reward. So steps individually don't produce instantaneous rewards. Now, after 0 iterations, well, all values are 0. That's v sub 0 of s, which we know is 0. Now, in the first iteration, we get the terminal values. And let's move forward. Now, as we keep going, you see that these values are changing rapidly, but these changes become smaller after the 10th iteration. And you can see the difference between the 100th iteration and the 12th iteration is very small. One more thing to note is we now have the policy here. These arrows are essentially the policy. These arrows are the actions prescribed by the policy. You can see that from the 9th iteration or the 10th iteration, they don't change all the way to the 100th iteration. So we could have stopped this value iteration process after 10 iterations. So an alternative approach for optimal values is policy iteration. The first step in policy iteration is policy evaluation. Calculate utilities for some fixed policy. And it's not the same as optimal utilities. We're dealing with pi, not pi star, until convergence. And in step 2, we improve our fixed policy. We update the policy using one step look ahead with resulting converged, yet not optimal utilities as future values. What does it look mathematically? And we repeat these steps until policy converges. So what does it look like? We'll get to that in a second. This is called policy iteration. It's still optimal. We still get to the optimal policy, but it can converge much faster under some conditions. So for fixed current policy pi, find values with policy evaluation. How? We iterate until values converge. We iterate over what? We iterate over this Bellman setup. We iterate, it means that we increment k in each iteration and calculate this value in the beginning. V0 of s prime of s is always 0, and we keep going until the values converge, which means that there's no change in values from v sub k to v sub k plus 1. Then there's the improvement process. For fixed values, get a better policy using policy extraction. So now you're going to extract a policy from this new value function. You're going to say our new estimate of the optimal policy, pi sub I plus 1, our I plus 1th estimate of the optimal policy function is now the argmax. This is the same formulation for policy extraction from value functions, but see that in here we have v pi sub I. So this is the value calculated by following policy pi I. And now we keep updating our v estimates, our v's and pi estimates until pi converges. Again, what do I mean by convergence? How do we know that pi has converged? If it doesn't change for a number of consecutive updates, it means that it has stabilized and converged. This is This is just a rule of thumb for convergence. Of course, it has a more concrete mathematical definition that you're all familiar with. Now, let's do a quick comparison. I know that the class time is over, but bear with me for a few more minutes so that we can finish this topic. Both value iteration and policy iteration compute the same thing. They are all calculating the optimal values. In value iteration, every iteration updates both the values and implicitly the policy. This is interesting. There is no explicit mention of the policy in value iteration, and this is similar to the formulation of the value iteration. But as you keep updating the value function, you're essentially updating implicitly, not explicitly, updating the policy as well. This is an important thing to remember when we start talking about off-policy and on-policy methods in reinforcement learning. Now, we don't track the policy in value iteration, but taking the max over actions implicitly recomputes it. In policy iteration, we do several passes that update utilities with fixed policy, and each pass is fast because we consider only one action, not all of them. Remember, it's just the action prescribed by that fixed policy. We are not exploring all possible actions. There is no max over A in this value iteration, this policy iteration step. After the policy is evaluated, a new policy is chosen, which is slow like a value iteration pass. The new policy will be better, or if it's not better, it is the same as before, which means that we've converged. These are both instances of dynamic programming for solving MDPs. If you're not familiar with dynamic programming, it's okay. You will read a bit about them in the notes that are provided for this module. And we will talk about dynamic programming a bit more when we get to reinforcement learning. But for those of you who come from a computer science background, you should be familiar with dynamic programming from your algorithms course, at least. Now, let's summarize. For MDP algorithms, we want to compute the optimal values. If we want to compute the optimal values, we use value iteration or policy iteration. If we want to compute values for a particular policy, we use policy evaluation. To turn your values into a policy, we use policy extraction, which is a one-step look ahead in the expect-max formulation. These all look the same, which is because, well, they basically are the same. They are all variations of Bellman updates. Remember that Bellman equation? That Bellman equation is also known as a Bellman update because it recursively updates our estimate of a function or a value. They all use one-step look-ahead expect-max fragments. They differ only whether we plug in a fixed policy or max over actions. All right, so we are done with the lecture today. If you have any questions, I'm at your service. Otherwise, it's okay if you leave. Next time, we are going to start our discussion on reinforcement learning. Thank you very much. Now, if you have any questions,